Welcome. Uh, so let me start with like you've already introduced me. I just wanted to know. So I am currently working in Google Bard. So I just wanted to know like how many folks have actually tried out Bard. You can raise your hands. Whoever has actually tried or heard at least of Bard, if not even used. Just one. Okay. That would be like a little surprising. Okay. Now I see more hands. So, yeah. Okay. Good to know. So, let me share my screen. Let me know once you can see. Yeah. Are you able to see the slides?
Yes, yes.
Okay. Thank you for confirming. Um, so, all the large language models that we hear about today, uh, all of them are based on an architecture which is called transformers. So today I'm going to talk about how the evolution of an LP has been. So some of the parts I think would be kind of overlapping is what I heard from the previous session. So I'll not like deep dive into it. Uh, but yeah, let me start with like a very famous quote from Andrew Ng. So he is, for those who might not know, he is like a leading figure in the field of AI, and he mentions that AI is the new electricity. So which kind of highlights the profound impact AI has already made and is expected to have across various industries and across various aspects of our lives. So what he mentions is just as electricity transformed almost everything 100 years ago, be it transportation, communication, or countless other areas, today there is a hard time thinking of an industry which AI would potentially like not transform. And this transformative power of AI, where does it really come from? It comes from its ability to learn and adapt from data and then make intelligent decisions from it. Um, so even if we see today, AI has actually reshaped the way we work, the way we interact with the world, and the way we solve problems. So be it healthcare, be it finance, retail, like in a lot of industries, we already see how much AI is being used. So just giving like a quick example. So for example, if we talk about healthcare, it is being used to design drug discovery algorithms, to develop diagnostic tools, to analyze medical images, learn patterns from it, and it is even used to assist with surgical procedures, right? So as AI continues to develop more and even mature more, we'll see that its impact is going to be even more pervasive and profound, shaping like the future of our work, shaping the future of commerce, or even like the future of society as a whole. So now coming to like one of the very famous words of the year, which has been like Gen AI, which stands for generative AI. So this is a revolutionary branch of artificial intelligence, and it's like a rapidly evolving field with wide range of applications and benefits. What this field focuses on is developing models which are capable of producing human-like content. So that content could be anything. It could be text, it could be images, it could be audio, video, anything. So the idea here is that it bridges the gap between machines and human like expression, paving the path for like a plethora of applications, right? So I think you guys would also have used Gen AI in one place or the other. So like would love to know like in what all places have you actually used Gen AI? You can unmute and speak. Anyone? You would have used, right? You would have, if you've used Chat GPT or Bard, that's a direct application of Gen AI. Okay, I don't hear an answer. So I'll probably go ahead. So you can use it for maybe content creation, maybe for like you want some content for your slides for a project or for virtual assistants. Um, let's say you want to translate languages, you could use it for that. Like an example I saw in the previous session was related to it, which was translating from English to Kannada, right? So, a very simple analogy to understand what Gen AI is comparing it to a child. So, imagine it being a child who's learning to create. You give that child a blank slate, and as it is exposed and as you make the child learn uh, the rules of the world or expose it more to what the world looks like, the child is able to create something beautiful. So similarly, generative AI, as you expose it to more data, it begins to learn the rules and patterns of the world. And once it has learned those patterns, it can start to generate new content. Then that content will basically be consistent with the patterns and the rules that it has learned. So now starting with the evolution of NLP. So in 1950s, it started with the rule-based systems. So they were basically very early days of NLP, completely dominated by rule-based systems. So they rely completely on a predefined set of rules. So there are some handcrafted rules and patterns which were used to analyze and process language. Now, a very small, like naive example of it could be that let's say if I write some if and else saying that if the word is ending with ing, it is a verb. So that becomes a rule. So this method seems to be like effective for very, very limited tasks, which could include something like parsing simple sentences. Um, but this method seems to be like very, very rigid and inflexible, right? And it even struggles to understand the semantic meaning or even handle like the complexities and the variability and the nuances of what natural language has to offer. So these limitations of rule-based systems um, basically formed and led to the advancements and led to methods like some statistical methods or deep learning methods, and then ultimately then there came transformers. So now talking about the second method, which is bag of words. So this again is like a very simple method where what you do is every document, every text document is represented by a vector. Now, sorry, is there some question? Okay. Uh, so every vector, which is every vector will have a dimension, and each dimension is basically each word in the vocabulary. And the value at that dimension is the frequency, that is the number of times that particular word has appeared in the document. So let's look at this example. Example number one. So imagine this one is basically a text document which says John likes to watch movies. Mary likes movies too. So this is one document, and we want to create a bag of words vector. So this BOW1 represents the vector corresponding to this text document one. So if you see, there are like 7 unique words in it. So the vocabulary size is 7 here, and this corresponds, and the value corresponds to the number of times this particular every word has come in this document. And the same goes for document number 2. So if you see here, one of the major limitations is that this method completely ignores the order of the words in which they are coming in the document and also the context of words. So let me take an example. Let's say there is one text document which says, I like this movie. And there is another text document which says, I don't like this movie. And if you create bag of words for both of these documents, so the bag of words will be very, very close to each other because there is only a difference of one word between the two, right? So this could lead to actually inaccurate representations, because both of these sentences or both of these documents are literally saying the opposite thing. So that becomes like one of the major limitations here. Um, can you think of or come up with, like, which you see any other limitation which this method has? Anyone? Any guess? This has to be more interactive. You can guess, it can be wrong. That should be fine. Yeah, please go ahead. Whoever has raised their hand.
Actually, they have written on the chat box.
Is it? Okay. Okay, I cannot see on the chat box. Okay. I think the picture in picture mode would help, I guess.
Yeah, I can read.
Yeah, sure. The size of the bag of words.
Yes.
Okay, what is the size when you refer to it? You can unmute and speak probably. That would be easier.
Size is number of elements.
Okay. So I am assuming that when you like size, meaning the size of the vector of this bag of words. Um, so that is absolutely correct. So if the vocabulary size is maybe very, very big, it's 50,000 or maybe even 1 lakh. So the vector size would be extremely big in that case. So if we want to learn, like if we want to train a machine learning model on top of such a big vector, it could be computationally very expensive to train such a model and then use it. So coming to the next method, which is TF-IDF, which stands for term frequency, inverse document frequency. So this is basically an extension of the bag of words method, and it is a much more sophisticated method and at least an effective representation of text data in comparison to what bag of words had to offer. So along with seeing what the frequency of a word is in a document, it also takes into account how rare the word is across a collection of documents. So the idea over here is that if a word is very, very common, we should give it lesser weightage. And if a word is rare, then we should give it higher weightage. Now, let's try to understand it using an example. Again, we have two documents. Now, the two documents are very similar to each other. But the difference is that the first document contains the word the, which occurs only 2 times. And then in the second document, the word the occurs maybe 25 times. So if you see, these two vectors are far because of the frequency of the in the two. So ideally, this the should not contribute a lot when we see that these two documents are similar or not. And that is where TF-IDF comes in. So it should give very less weightage to words like the. So this weighting mechanism helps emphasize on words that are actually more important to distinguish documents from each other. So now let's look at the formula for TF-IDF. So the first term is TF-T comma D, which stands for frequency of term T in document D, which is similar, which was there in bag of words also. The new thing is this IDF-T. So let's look at the formula here, which stands for log of n divided by df of t. N is the total number of documents that we have, and DFT stands for in how many documents this term T is present. So let's go back to the same example where we had two documents. We have the term the, one has the coming 2 times and one has the coming 25 times. So if you see the total number of documents, n will be equal to 2 here, since there are only 2 documents. And if we talk about the term the, it is appearing in both the documents. So df of t will be equal to 2. So 2 divided by 2 would give us 1, and then log 1 becomes 0. So the weight, basically this IDF is calculating the weight. So it will give very, very small weight for the terms which are very, very common. So this method TF-IDF solved like one issue which is there in bag of words. But if we come to what the size of the vector is, or the order of words, or like taking into consideration the context of those words, or taking the semantic meaning of the word, so all of these things are still missing in the TF-IDF method, and these are not really getting resolved. So that is where this next method comes into picture, which is word to vec. So this is a neural network based algorithm to generate and to learn embeddings for words which are based on what the surrounding words are. So we'll understand this method in detail, but the idea here is that what we are trying to learn is vector representation of words, and they will capture semantic and syntactic relationship between words. So there's a very famous quote by J.R. Firth, which kind of aligns with how this word to vec method works. So it says that you shall know a word by the company it keeps. So let's say I want to learn a meaning of a new word. So one way I could do that is I could take a few sentences in which that particular word is there, and I can read those few sentences and try to figure out what the meaning of it is. That is one way, and word to vec actually works in a very similar manner. So the model is trained on a large corpus of text, and then it learns to represent words as vectors. And the overall idea over here is that if the words are very semantically similar, then the vectors of it would be very close to each other in the vector space. And if the words are semantically dissimilar, then the vectors will be far apart. So one example is, let's say the two words dog and cat, both are animals, right? So their vectors would be comparatively closer to each other. And let's say if you say dog and house, so those two vectors of these two words would be kind of far apart from each other. So what is seen is that the embeddings which word to vec learns, the it shows like very interesting patterns. So it shows linguistic regularities and patterns, and it kind of has some patterns which lead to linear translations. So if you add the vector embeddings learned from this method, it leads to something very useful. So if you look at this image, it shows the vectors for countries and capitals. So let's say if you subtract vector of Spain from vector of Madrid and add vector of France, the vector which comes out to be, if you see which word is it closest to, it comes out to be vector of Paris, which is actually the capital for France. So now let's look at how how is this model really trained. So the first step would be to generate the training data for it. Now the method to generate the training data is as follows. So the step one is you basically get a lot of text data, and then you decide a window size. So let's say we take a window size of 4. Now all we need to do is we need to just slide through this window. So we'll get set of 4 words continuously across all the text data that we have. Basically those are the training examples for our model. Now there are two variants of this method. One is CBOW, which stands for continuous bag of words, and the other one is skipgram, which we are going to cover now. Yeah, please go ahead.
These are
Hello. Is there a question or should I move ahead? Yeah, please go ahead. Can you please unmute and ask the question?
There is an echo. Please check the chat window.
Yeah, I am going to cover all the methods. So I hope that is okay. Okay. Yeah. So in continuous bag of words, the idea here is that you try to predict the target word based on whatever surrounding words are there in the window. So let's see this example. So the input sentence here is the quick brown fox jumps over the lazy dog. And now the window size is 3. So basically the training samples would look something like the quick brown fox jumps and so on. So now if your current word and if let's say your target word is fox, so what CBOW model would try to do is it would try to predict fox given the context words which are brown and jumps. Now in the skipgram, it does the exact opposite. So it tries to predict the context words given a target word. So the same example, now the target word is fox. So skipgram would try to predict brown and jumps over here. So I think this picture kind of makes it more clear. So here if you see the window size is 5. So it takes in these 5 methods, these 5 words in total. So there are 4 in the context and then this one is the target. So CBOW tries to predict WT given these context words, and in skipgram it takes the target word which is WT and tries to predict these 4 context words. So now coming to the another method which is RNNs, which I think has been covered in the previous lecture also, so I'll not like deep dive into it, but just for context. So whenever you read a sentence or whenever let's say you're reading this slide, you try to understand each word based on what your understanding is from the previous words. So you just don't suddenly start thinking from scratch. So your thoughts have persistence. But traditional neural networks cannot do that, and this is kind of a shortcoming in traditional neural networks or feed forward based neural networks, that they do not really take into account the structure which is there in the sequential data. So what RNNs do is RNNs are basically neural networks with loops in them. So this image shows it that all of these hidden states for different observations, they have dependencies, and the hidden state at each step basically depends on the hidden states of the previous steps. So for example, let's say you're trying to predict some movie event at step T. So you can basically depend on uh, whatever states there were in the movie before that. So this HT basically acts as a memory and it helps us remember whatever has happened up to step T. Now in this image, if you see, there is just one hidden layer. So RNNs can obviously be extended to having more than one hidden layer. So it's not necessary that it would have only one. Now there are like enormous applications of RNN. The first one being the one-to-many case where the input is one, but the output could be many. So this example is of image captioning where there is an image input which goes in and the output is words in the image caption. So it basically gives a caption out. The second one is the case where it is many to one. So the input is words in the document, and the overall problem statement here is to classify that document. So let's say there are a couple of documents and you want to classify them into various categories, for example, news, movies, etc. So here the output is just one, which is the class or the label of that document. Then there comes the many to many case, where one example is machine translation, which is translating from one sentence, like from one language into another. So here the input goes in, which is in English, and the output is in Hindi. Now, another application in the many to many case could be that, let's say you want to label each frame in a video. So you'll have like multiple inputs where you are sending in frames in a video, and it is out, and it has to output labels for each frame. Now let's try to see what are the limitations in this method, which is RNNs. So let's say you're trying to predict the last word in this text. So the sentence is as follows: I grew up in France, something, something. So, and then there is I speak fluent, and the last word is what you want to predict, which is French. So if you look at just the recent words, so based on that, the next word you can predict is probably a name of a language. But if you really want to know what the exact language is, and if you want to drill down and narrow down to which language, you really need the context France. Now, without this context France, you really cannot predict the word French. So, when you need the context from further back, then it becomes a problem for RNN. So, if the gap between the relevant information that you need and the point where it is needed, if that becomes very, very large, then RNNs are unable to learn and connect this information. Now, if you look at this example, so let's say the information that you need is from x0 and you need it at this place, which is ht plus 1, and the gap is large. So the updates happen in such a way that there are like repeated multiplications in the way updates happen, which can cause the gradients to either vanish or explode. So a simple way to understand it is that whatever your new inputs are, they tend to overwrite the activations of the previous hidden states, right? So as you move far and far away in the sequence, the sensitivity of the hidden states basically becomes weaker and weaker. And that is where this next architecture, which is LSTMs, come into picture. So LSTM stands for long short-term memory. Wouldn't deep dive into it. So they are like a special kind of RNN, and they are explicitly designed to avoid this long range dependency problem, basically. And the overall idea over here is that a new concept was introduced in this architecture, which is gates. So they basically help us remember and forget information selectively. So you basically decide at every step through the gates how much relevant information is there which you want to pass on, and what is the irrelevant information which you want to forget. So if you see over here, there are these three things: IT, FT, and OT. So IT basically tells how much do you want to take in the local context, FT tells you how much do you want to forget the previous context, and OT tells you how much do you want to output. CT is the cell state where you use IT and FT, and then ultimately you calculate what the hidden state has to be based on whatever your CT is and what value OT gives you. So if you see over here, the state updates are now additive and not multiplicative, which kind of helps uh, avoid this long range dependency problem to some extent. But then after this, there were a few architectures like GRUs came in, and then in 2017 there came this transformer architecture, which has revolutionized the field of NLP, and it has been like a dominant architecture um, used for a wide range of benchmarks. It had given state of the art results across a lot of benchmarks, including machine translation, question answering, text summarization, etc. So let's try to understand how could transformers perform, and what is exactly there in a transformer. So we'll decode the architecture of transformer now. The core of this architecture is basically the attention mechanism, which helps and allows the network to focus on the most relevant words in a sentence while it is processing it and while it is making predictions. So this seems to be much more powerful than the traditional NLP models, since it does not struggle to handle the complexities and nuances of natural language, and it is able to handle the long range dependency problem completely. So this is like the first sequence transduction model which completely relies on attention, and it replaces the recurrent layers with something called as multi-headed self-attention, and I'll cover what each of the terms mean. So let's quickly look at the overall, like a very high level overview of how transformers look like. So we'll take the example of machine translation where we are translating French into English. So this is the French input which goes in, and then there is a stack of 6 identical encoder layers. So this encoder is basically responsible for processing the input sequence and producing a representation of the input here. Now, once these 6 transformers, so the output of the first encoder goes into the second and so on, and the final output from the 6th encoder is utilized on the right hand side. So here if you see again, there is a stack of 6 identical decoder layers. Now here decoder is responsible for generating the output sequence, which is basically from the input representation which is generated by the encoder. So now let's look at the architecture of encoder and decoder in detail. So if we see, the inputs go in and there is this input embedding which is added with a positional encoding here, and a similar thing happens for the outputs as well. The reason why we need a positional encoding, which we did not really use in the RNNs or LSTM kind of architectures, is that over there we had recurrent layers. The hidden states were connected to each other. But here, let's say if the input is I am a student, so all of these words go in parallel. So somehow the architecture or the structure should actually know which position every word belongs to, and that is where this positional encoding comes into picture. So now, after this, we have 2 layers in the encoder and we have 3 layers in the decoder. Now the 2 layers of the encoder are multi-head self-attention, which basically helps focus on the most important parts in the input sequence. And then there is this feed forward layer. So this exact same feed forward is independently applied to each position. What that means is, let's say the input is I am a student. So there are 4 words. So this feed forward network is applied to all these 4 positions. So for all these 4 words, there'll be a feed forward neural network, which will be independent of each other. Now, if you see in the decoder, there are 3 layers in which the 2 layers are similar, which is the feed forward and the multi-head attention. If you see over here, it says masked multi-head attention. So there is like a slight modification in comparison to what we do in the encoder versus the decoder, and which I'll cover in the next slide. So there is this layer in between the two, which is not present in the encoder layer. So again, this is a multi-head attention, but the difference here is that the input from, like basically the output of the encoder is the input in this layer, which is different. So how it helps is, it helps the decoder to focus on the relevant parts of the input sequence. So now coming to the other parts which are remaining in the encoder. So till now, what we have seen is we'll have a stack of 6 encoders. So this is just one encoder. This n is basically 6 in the base transformer. So there are 6 identical layers for the encoder. Now there is a multi-head self-attention layer, and then there is a fully connected feed-forward network, which is position-wise. Now what is remaining is this add and norm layer, which is basically a residual connection is there, which is wrapping around both of these sublayers, and that is followed by layer normalization. So if you see the output of each sublayer, it it looks something like layer norm of x plus sublayer of x. So sublayer of x is the function which would be implemented either by the multi-head attention layer or the feed forward layer. Okay. So the place where these residual connections help us is they help us to prevent forgetting of the information while it is processing the input sequence. Now, if you see, ultimately, all of these are vectors. So the sublayer of x output will also be a vector, and this x is also a vector. And if we want to add these two vectors, so to facilitate this, we need these sizes, vector sizes, to be the same. So all the output of all the sublayers in the model plus the embedding layer output is of the same dimension. Now in this paper, what they've taken that to be is 512. Now coming to the decoder. So like I spoke about before, there is a slight modification in the first layer in the decoder. So basically the difference or the modification here is that we want to prevent the positions which are subsequent to I to not really attend. So what that means here is that, let's say I want, like, my final output has to be I am a student, and let's say I am at the word am. So I am at the second word which is predicted, and now I want to predict the third word. So when I want to predict the third word, I shouldn't be attending. So my decoder should not be able to see the third word and the fourth word in the sentence. So basically, the decoder should be prevented from attending to all the subsequent positions. And that is where this masking comes into picture. And this, if you see the residual connections, this add and norm layer, similar to what was there in the encoder, it is also employed in the decoder, and it is employed for all the 3 sublayers over here. And then finally we have a linear and a softmax layer, which basically gives us the final output probabilities. So one simple way to get a particular word from the probability is taking the whatever the highest probability is. So let's say our vocabulary size is, let's say, 10 words, and am has the word which has the highest probability. So we select that word and say that this will be our output at the step 2. So now coming to the term attention, as I've used it constantly. So attention is basically a mechanism which is allowing the model to focus on the most relevant parts. And attention is something which is basically enabling the model to capture these long range dependencies between words, which is extremely crucial for understanding and handling those complexities of natural language. We'll cover an example in the next slide, which I think which will make it more clear. But the idea is that when we are reading a sentence and trying to understand maybe some particular word, we focus on some specific words more than the others while we are reading it. So that is something which attention is also doing. So attention is also referring to the ability of the model that it also will focus on some specific parts while it is creating an encoding of the input. So let's look at this example. So the following sentence is, the cat didn't eat the food because it was not hungry. So let's say we want to translate this input sentence. Let's look at the word it. So what does this word it refer to? Does it refer to the word cat or does it refer to the word food? So a human can easily tell that this word it is referring to cat and not food. But how do we make a model stress while it is looking at the word it? That is where self attention helps us. So, self attention allows it to associate the word it with the word cat. And basically, so as the model is processing each and every word, so basically each position in the input sequence, self attention is allowing it to look at other positions in the input sequence. So it gives clues that helps lead to a better encoding for this word, and so it would hold true for each of the words in the input. So this is a screenshot which I took from the paper itself, which is attention is all you need. So the sentence says it is in this spirit that a majority of American governments have passed new laws since 2009, making the registration or voting process more difficult. So if you look at the word making, the and all of these are how much of the how much are we attending to all of the words. So we are attending to the words 2009 and the word making itself, which makes sense, and then the words more and difficult, while we are creating an encoding for the word making based on self attention. So if like a typical self attention mechanism um, has these following steps, starting with the first one, which is there is this input sequence, you break it down into words or subwords. The second step is, let's say we are trying to calculate self attention for the word it. So what we do is we calculate the similarity score between this word it and all the other words in the input sequence. Now, once we have these similarity scores with us, these scores basically are used to weight all the words while we create a representation for the word it. Now, after we have these similarity scores, we calculate a weighted sum, which is the final output. So, this final output is basically the representation of the input sequence, and it is able to capture relationship between all the words in the input sequence, right? So overall, like this was about self attention, but if I speak about what attention is, so a formal definition of it is as follows. So there is something called QKV triplet, which is query, key, and value. So attention is defined as follows, that you try to map a QKV to an output, and where all of these four, query, key, value, and the output, all are vectors. Now the output ultimately is like a weighted sum of the values. So this term, so you can think of it as like two terms. The first one is softmax term and the second one is V. So this softmax term is basically telling us the weights, right? So if you see, this QK transpose is basically a dot product, which is giving us how much importance should we give to each word. Another thing to note is, one extra thing this paper has done is they are dividing it by the square root of dimension of k. So the reason they are like they mention is that there is a chance that the dot product of the query and key could grow very large in magnitude, and it could lead to the softmax to be in regions where the gradients are very very small, and that is where um, dividing it by the square root of dk actually helps. So let's look at this example, and so here we have these two words. So imagine the input sequence being these two words, which is thinking machines. So the first thing that we need are the two embeddings for the two. So x1 and x2 are the two embeddings respectively. And now we have queries, keys, and values. So the way we calculate these query, key, and values are that we'll have some weights. So there'll be basically three matrices, WQ, WK, and WV, which will be learned. So we'll multiply embeddings with those matrices, and and that is when we get query key and values. Now once we have all these four, let's say we want to get the embedding for thinking, for the word thinking. So now to calculate the score, we fix the query and we calculate the score by doing dot product of Q1 and K1 and then Q1 and K2. So let's say, just taking an example, that let's say the values come out to be 112 and 96. Now once we have these scores based on the formula, we'll divide it by the square root of the dimension, which gives us 14 and 12 respectively. Now we take the softmax, and this is the exact score. So basically, while we are trying to represent the word thinking, the score for this word comes out to be 0.88, and the score for the other word in the input sequence, which is machine, comes out to be 0.12. So now what is the exact representation of this word thinking? So what we do is we'll multiply 0.88 by V1 and plus 0.12 times V2. And this finally gives us Z1, which is the output from this whole self-attention mechanism. And now, similarly, we can also calculate the embedding out from the word machines. So over here, we'll fix this Q2 and we'll do everything similarly. The only difference would be that we'll try to calculate the scores using doing the dot product of Q2 and K1 and then Q2 and K2, and everything else will be kind of similar, and it will then give us scores that while we are representing the word machines, how much importance should we give to the word machines and how much importance should we give to the word thinking. So this example only takes like two words, but the input sequence could be bigger. So it would basically, so let's take this example. So over here, what it would do is it would take and it would get a score for all the possible pairs. So it would be it and the, and then it and cat, and so on. So now, here in this example, we've seen that queries, keys, and values we've taken as vectors, but while implementing, we take a set of queries, keys, and values. So this is what the representation of it would be in the matrix form. So now, if we see overall, there are three types of attention used in this paper. One is self-attention used in the encoder. The second one is self-attention used in the decoder. And the third one, which is encoder-decoder attention, which, if you remember, which occurred in the middle layer in the decoder. So let me speak about the self-attention in the encoder first. So self-attention, so the word self basically reflects that all the keys, queries, and values, everything is coming from the same place. So in the encoder case, it is coming from the output of the previous layer of the encoder, right? And this layer is basically helping us that each position in the encoder is able to attend to all the other positions in the previous layer of the encoder, because that is where the input is coming from, right? And now the other one is self-attention in the decoder, which is the first layer in the decoder. And this is again very similar to what I spoke about in the encoder. So all the keys, queries, and values again are coming from the same place. The only difference is that it takes the output from the previous layer of the decoder, obviously, and not from the encoder. And this allows each position in the decoder to attend to all other positions, but only up to that position and not, so there is this masking which helps to prevent attending to the subsequent positions. And now talking about the middle layer which is there in the decoder, which takes into account the encoder decoder attention. So here what happens is the queries are coming from the previous decoder layer and the keys and values are coming from the output of the encoder. So the place where it helps is that every position in the decoder is able to attend to all the positions in the input sequence. And I think this image kind of reflects that as well, just going back once. So if you see this input, these queries are coming from the previous layer of the decoder, and The keys and values are coming from the output of this encoder. So now let's talk about multi-head attention. So it is something very, very similar to what we have just spoken about. The only difference is that there are like multiple attention heads which are implemented in parallel. And when we get the outputs of all these attention heads, all of these are then concatenated together. So if you see in this formula, let's say the output of head 1 is something, and then head 2, and so on till head h. So everything that comes in, we concatenate all of it, and then we multiply it by a weight matrix to get our final output. So what this paper shows is they've taken specifically that they've taken 8 attention heads, and it seems to improve the performance of the transformers across a wide range of NLP tasks. Now, where it helps is it allows the model to basically jointly attend to information which is coming from different representation subspaces from basically different positions. So let's see this visualization, which makes it like much more, it becomes much more clear from this picture. So this is our input sequence, which is thinking machines. We embed each word. This is our X. Now, if we need 8 attention heads, it means we need 8 QKV matrices. And if we need 8 QKV matrices, we need again, like we need 8 weight matrices also to actually get these QKV. So our second step would be to have this WQ, WK, and WV from 0 till 7, since we have 8 attention heads. Once we have these, we multiply x with these, and we get these QKVs from 0 to 7. Now, once we have these, based on what the formula is, we can get the self-attention. So we'll basically get the output from this from Z0 to Z7. Now what we can do is we can concatenate all of these and then multiply it by a weight matrix to get our final output, which is Z. Now let's look at like the overall visualization of how the transformers are working with this example. So this input sentence contains these 3 words. Now we have these 3 embeddings corresponding to these 3 words, and we add positional encodings to it. And then there is this encoder. So we pass it through this. So here it is not shown to have like 6 encoders, but you can imagine having 6 stack of 6 encoders here, and same goes for the decoder layer. So this encoder outputs these 3 embeddings. Now these are used in the decoder step. So over here in step 2, I think it has reached the end. So it'll go back again. So it starts with the word, it predicts the first word I, and then this I will go in and then predict the word am. And then this am will also go in and predict the third word, which is A, and so on. So the fourth word it predicts is the word student. And then the student goes in and then predicts a token, which is end of sentence. So that's a token with which you know that this is where you want to stop. So this architecture actually got better blue scores for this EN, for this English to German translation, and then from English to French translation, comparing it with the other methods. So this blue score basically represents how good the machine translated text is in comparison to if you compare it with some human written, some reference translation, which you already have. So in today's world, we see that there are like lot of large language models which are coming in. And overall, if we speak about it, there are like 3 types of architectures. One is which only use the encoder part. So they are called encoder only models. So with whatever we have learned in this session, it will only take the encoder part of it. And the models which belong to this category include BERT, Roberta, Distal BERT, BioBERT, and so on. And then there comes this second category, which is the decoder only models, which only use the decoder from this architecture, which includes the GPT series, which is like including GPT-3, GPT-4, and then the Palm model, Lambda, Llama model, and all of these. And then there is this third category, which uses both encoder and decoder models, which include BART, T5, T0, FLAN T5, etc. So there is this very nice tree in this survey paper, and probably a very good paper to actually go through, uh, which basically shows the timeline of which model came when, by which organization, and then which category does it belong to. So probably a good read it would be. So yeah, I think that's all from my side, and I'll be open for questions now. Are there any questions?
Yes, yes. Hello, ma'am.
Yeah.
Like, I had a simple doubt. Like, is GAN a generative AI?
GAN produces. Where have you used GAN? Is my first question.
Like a generative adversarial nets. Like these are used to generate images, right?
Yeah, so that's a generative. If it is generative, then it is part of generative AI.
Not only text generation models are generative AI, but also these GANs will be coming under generative AI.
Yeah, so if you remember in my starting slides, I mentioned that generative AI means focusing on models which generate human-like content. It could be text, it could be images, it could be audio, it could be video.
Okay.
It could be anything.
Okay. Regarding these LLMs, like particularly the GPT model, which is decoder only model, after some series like GPT-2 and GPT-3, what they are saying is like only pre-training is we are doing, and not they are saying some active learning like zero shot and like few shot, given some context and asking questions, it is able to perform well than some fine tune on downstream tasks. How do you think like what how only pre-training helps these like it also like outperforms the fine tune task? What is that? Next.
So the large language model, so it depends on one, how many parameters that model has and the way it has been trained, right? So the pre-training, which is also happening, there are a lot of things which are going in, okay? One thing is the way they are generating the data for that model. So if the data that they have generated has immense knowledge about the world, so it already has all the knowledge in it that it is able to perform the way it is today. That is one reason, okay? The other thing is it's not just simple training which they are doing. They are using something called, one thing is reinforcement learning from human feedback, which is a very very strong thing to do, which potentially maybe a model which you're training on a downstream task is not doing currently, right? So there are various methods in which they are doing that retraining itself. Yeah.
Like the transform paper is like its main use case. The paper written on it is related to translation tasks like from English to German, right? Now these like there is a attention like a cross attention like a encoder decoder attention in that, which helps mainly for the translation. But after these like decoder only models are able to like are they able to do well on the translation which only contains the masked self attention?
Come again, are you saying that you want to modify the decoder architecture, or are you saying that whatever decoder models are there, how well can they perform on translation tasks?
Yeah, already like GPT or Flam like but are they very well means how are they able to perform well on this translation task without having this cross attention which is introduced in the transformer?
Okay, so it depends on one, how they are trained, right? So in the encoder decoder part, you have a specific input, you have a specific output, and you know the input has to be passed through the encoder and the output you'll get through the decoder, right? But how a decoder is basically trained is you want to predict the next word. That's how it is trained, right?
Yeah.
So, but the amount of data it is fed with is how it learns. So let's say you say a sentence, can you translate this English sentence into Hindi? You give the English sentence, right? And you ask the decoder, this is while training. Okay. So this is your training set, and you ask it to generate a sentence in Hindi over here, right? And if you've trained this model in a way, why will it not be able to translate well? No? So there are like different pre-training objectives used in, there are some specific pre-training objectives used in encoder only models, and then some specific pre-training objectives used in decoder only models, but they are designed in a way that it is able to work well.
It understands the world around us and all the languages while training only. Is
Yeah.
that?
Yeah.
And suppose I want to fine tune some of the if I am having this large data set which is like 8 GB or something, how and I'm using resources on like 8 GB or 6 GB RAM, how am I able to load this data set while some fine tuning or something?
So one thing is, even like these models are so big that even loading them is a task, right? So there is this another stream of work in research which is going on, which kind of optimizes the models also. And the way you can fine tune a model, there is something called as LoRa. So there are a couple of methods which you can read about if you want to optimize, if you want to see how do I optimize while you want to fine tune.
That LoRa is like low rank some
Yeah.
parameter.
Yeah.
Like this last question, like related to Google, like Google recently released this Gemini model where it is using, now we can use that on Bard. Like it says like it is a multi-modal model. It has some modality, and what is this multi-modality? And that in technical report they haven't said architecture about it, and they said just it's a transformer. Like
Yeah, it is a transformer. So obviously, like even for images, there is this vision transformer which came in, and then there are architectures formed on top of a transformer. On top of a transformer. So everything, a base will always be a transformer. But exactly how it is trained, what is the data being used, what is the exact architecture are the kind of things which I cannot speak about here. Like I am not allowed to.
just say
So
about multimodal. What is that?
yeah, so you basically see one of the ways even you can learn it is, and it is not just specific to Gemini. If you go to Bard today, you add in an image, right? So one, it can generate images. Second, you can in your prompt add an image and it can give you the answer to it. All right. So it is being specifically trained to understand image to text and text to image, and then mix it even both. So that's the way the training data is created. And if you train the model to understand images today along with text, it will be able to, right? The way you have to train it might be different, and I cannot speak like more about it because I'm not allowed to.
Okay, and so the results are saying about this chain of thought process. Whereas ChatGPT uses 5 shot or few shot. What is this chain of thought on that Gemini?
So are you asking me the performance of chain of thought on Gemini?
What like prompting process? What is this chain of thought? Like how it
Okay,
is
in
different from?
general, okay. Yeah, so basically, one simple way to understand it is you have a large language model, you give it a prompt, it gives you an answer, right? So let's say you want to perform a very specific task and you're not showing the large language model any example for it, then it is zero shot. You are directly saying, this is the question, give me the answer to it. I will not show you any example how to do it. still you are expecting the model to respond in the right manner, right? If you give one example, it is one shot. If you give it two examples and show it, okay, this is the input, this is the output, this is what I want, right? So then that is two shot, and so on. So then there came in like chain of thought prompting, which is if you see that for mathematical and reasoning cases, large language models today do not work that well. And that is where this chain of thought prompting idea came in, which says that along with giving the question, so it's like, let's say there's a maths problem from class 10th. Okay, some one boy has these many apples, the other has those many apples. Now what will be the output? Something like that. Okay, now instead of telling the large language model the answer to it directly, that okay, the total sum will be 5, instead of saying that, can the chain of thought says that explain how that answer really came. So basically explain the thought that okay, this person had 2 apples, the second had 3 apples, a person took something from the other, so we are left with these many apples. So this is the whole thought behind how that answer really came. So if you give this exact explanation, which is basically the chain of thought, if you give this whole thought process to the model is able to pick it up better. So if you give this chain of thought, it will be able to answer you better. And it is seen that chain of thought prompting works much more better than 0, 1, or 2 shot, especially in the maths and reasoning cases.
Okay, got it. Thank you. That's it.
Thank you so much. Yeah,
So-
I think, yeah.
So in continuous in the previous question, so I would like to ask, like recently your company has introduced this Gemini model, and your company is claiming that the performance of this model is much better than the ChatGPT 4. So I would like to know what are the parameters or what are the matrices through which you are evaluating that the performance of the Gemini is much better than the ChatGPT 4. But still, if you know the current scenario, if you see that the still like people, like the audience of people, they are not attracted towards the Gemini or Bird models, but still like people are using ChatGPT mostly, if you talk about. So could you just highlight what are those parameters or matrices?
So I think I haven't even gone through the technical report of the Gemini model, which has come in. But we have personally seen it performing better than at least ChatGPT, like, because we have access to it. So probably a technical report could answer this question better than me, since I have not been a part of Gemini. Like, I work in Bard multilingual, so
Yes.
and that is where Gemini has not come in yet. So yeah, I think, sorry, but the technical report would answer the question better. But
Okay.
yeah, I think if they have claimed it,
Yes, yes.
it would work better. So there are like specific use cases. So if you see today, let's say some creativity use case where you're trying to write a story about something. Okay, there are certain use cases you see that Bard is working better than ChatGPT. And then there are use cases, for example, maybe coding, where GPT seems to get it right than Bard. So it's like one model is trying to do it all. Some places it does better, some places it does not. So I think that is kind of a difference which comes in. And I think they've evaluated in it on multiple data sets where they mention where it is better.
Okay, okay. Okay, still like we have some few more questions on the chat box, so I think you can see.
Yeah, sure. So there's something called as vision transformers, which works for images. And um, so they've combined like the CNN concept with the transformers. And in the pre-trained encoder model, like BERT, what modifications can be made through which we can change the functionality of the self-attention module. For example, if we have to change the self-attention method such that we can add some vector to the attention score vector before passing it. Yeah, so you need to implement it from scratch, right? You can implement it from scratch. So whatever output you get from the self attention, if you want to add some function on top of it, you definitely can. But then you have to do the whole of the pre-training and everything. And it, like, if you want to add something on top of it, then you really cannot use the pre-trained version. Then you can pre-train it yourself, which would be very, very heavy in terms of resources and the data. So I can probably like, please feel free to connect with me on LinkedIn, and if you have any questions, I can answer them offline as well. Since, like, I think there is a session from 6 for the next speaker.
Okay, so just one more question you can take. Like, could you discuss how feudal or positional encoder works on 2D and 3D data?
So it's just like, you can pick up that equation, which is, you can find the equation in the paper. Attention is all you need. It gives the details about the exact how it calculates the encoding, and then how does it add there. And at least for this paper, they have taken it on text. Um, right? And I think, yeah, I mean, what they overall do is simply um, calculate. I can go probably to the equation. um, yeah, so all they do is they take the positions and they do some sine of position divided by some constant to the power of 2 times I divided by d of model. So I think that's pretty straightforward, at least in this case. Yeah, but here the positions wouldn't be 2D, right? So that's a sentence, right? You can even take from, like, you can take a 1D here. And even when, let's say, for example, like, one simple way of doing it on 2D would be, you can actually make a 2D a 1D, right?